Chapter 25 is about pathogenic RNA viruses. So we're moving forward from DNA viruses. We start the chapter by addressing the fact that any permutation they can think of regarding the assembly of the genetic material in viruses has been incorporated by Mother Nature. We can dream it up, it has been done. So, for instance, you can see here that there are 4 types of RNA viruses, okay? Why? Because at most there's 4 different permutations in which RNA can be stored as a genetic material in a virus. And here they are. They can be positive single-stranded RNA, okay? Now, positive and negative implies the direction in which the RNA is read. If you can take that genetic material and place it on a ribosome and translate it directly into a protein, then that is said to be a positive RNA. However, if the RNA would not produce a protein, but instead you have to first synthesize its complementary strand, then that is the alternate, that is the complementary strand, and that is considered to be a negative strand. Again, the negative strand, if you were to place it on a ribosome, would not produce a protein because it is the complementary strand to the strand that would in fact synthesize a protein. So you can have positive RNA, you can have negative RNA, you can have retroviruses. Retroviruses are viruses in which their genetic material is RNA, but they have reverse transcriptase and allows it to go backwards in the central dogma from RNA to DNA. And then finally, another peculiar permutation is double-stranded DNA. So these 3 up here are single-stranded DNA, and then this one we have double-stranded DNA. And again, that's a rare and peculiar event because in most organisms, it is DNA that's double-stranded and RNA is typically single-stranded. But here, these viruses, through adaptation, have chosen to synthesize both the template and the complementary strand of DNA in an effort to maintain the integrity of the RNA. Okay. Let's see. In addition to these different ways in which the RNA is stored as a genetic material, we can also discern the identity of viruses based on their structure. I guess another way would say their morphology, okay? Whether or not they have an envelope. Remember, an envelope is typically a plasma membrane of the host that the virus envelops itself in, and it helps the virus circumvent the innate and the adaptive immune response. And then finally, the shapes of their capsid. So some capsids are icosahedral, some are helical. There's various shapes. As a matter of fact, in your summary this week, on the second summary, XX, I'm having you fold a virus so you can become acquainted with what an icosahedral shape is. So here we go. We start with single-strand positive single-strand RNA viruses, and we start with the picoRNA viridae. So pico really is a size, okay? If you're measuring something in the SI system, in the metric system, 10 to a negative third is milli, 10 to a negative sixth is micro, 10 to a negative ninth is nano, and 10 to a negative 12th is pico. So what the individuals that named this virus are trying to convey to their audience is that the average size of this virus is about 1 times 10 to the negative 12 meters. In other words, very small. Okay, so smallest of the animal viruses. Okay, let's see. Well, there's three significant genera here: the rhinovirus, the enterovirus, and the hepatovirus. Rhino, of course, dealing with the nose, so these are typically associated with respiratory infections. Entero, hopefully by now you know that entero means gut dwelling. Okay, so entero are really viruses that are transmitted by the fecal oral route. So as horrible as this sounds, this implies that the virus is coming from the gut, and somebody, due to lack of hygiene, transmitted that to somebody's mouth, maybe their own. And then finally, we have hepato, which are those viruses that attack the liver. Okay, we address the common cold. Okay, so the common cold is typically a consequence of the rhinovirus. Again, rhino meaning nose, so we're talking viruses that attack the respiratory system. And so one thing that's important to acknowledge is that there's over 100 different strains of rhinoviruses that cause common colds. And there's other types of viruses that are not rhinoviruses that are also responsible for producing common colds. So this is why we're never going to produce a vaccination against a common cold. It's never going to happen. We have over 100 different strains of viruses attacking us at any minute. It's very difficult for us to produce an immune response capable of handling that variability. And one of the things that's incredible is that these rhinoviruses have very good attachment proteins. So a single virus can actually be enough to initiate an infection, a cold. Quite incredible. Okay. Now we're moved from rhinoviruses to enteroviruses. Okay, so again, one of the things that's important to know this is that the name of the virus is because it's transmitted via the fecal oral route. And it's also important to know that enteroviruses, the particles multiply inside the host until the host cell ruptures or lyses. So consequently, enteroviruses are known to kill their host as part of their reproductive cycle. Okay. Now we move on to a type of enterovirus. There's Coxsackie A virus and Coxsackie B virus. Coxsackie is actually the name of where the virus was first isolated, which I believe was Coxsackie, New York. Okay. So we have these enteroviruses. Enterovirus A is responsible for producing these pathologies. So herpanglia, which is of course mouth blisters. The hand, foot, and mouth disease is a type of zoonotic disease that is common among children and infants. And acute hemorrhagic conjunctivitis. And I have found that scaring my students is very helpful. It brings their attention. So I'm going to do a quick search on Google here for hemorrhagic conjunctivitis. Bring up the images and put this on my little shared folder here. And look at this. Is that horrible? Okay, so this is not trivial stuff. This is something that can cause a lot of pain and discomfort and whoever's suffering from it. Okay, so that's to Coxsackie A virus. Again, that's hemorrhagic conjunctivitis. Here's Coxsackie B virus. Okay, so what is the manifestations of this Coxsackie B virus? It's associated with myocarditis, inflammation of the myocardia, and the pericardium. Okay, it causes a disease called pleurodynia, which is a malfunction of the lungs. Okay, and it is also a causative or suspected causative agent for diabetes, type 2 diabetes. Okay. Hopefully you're catching on to what the trend is here. Okay. And the trend is that all of these effects are associated with autoimmune responses. So viruses have this nasty tendency to infect a body, and whatever they do not kill, they disrupt. Okay. So these viruses have a tendency to disrupt the surface antigens of our tissues, and then those tissues are no longer recognizable to our own bodies, and autoimmune responses are launched. Okay, if that event happens in the heart, they end up with myocarditis or rheumatoid fever. If that happens in the pancreas, they end up with diabetes mellitus, type 2 diabetes. Okay, so this is a manifestation due to an immune response that is provoked by this, an autoimmune response that is provoked by this B virus. Both of them are known to cause meningitis, so that's supposed to convey what a terrible scourge both of these can become. Okay. Now we're moving to hepatitis A virus. Okay. Again, transmitted through the fecal-oral route, and it's important for you to become aware of the signs and symptoms associated with hepatitis A. Okay, fever, fatigue, nausea, anorexia. Remember, anorexia can manifest itself in multiple ways. It's not only the absence of hunger. It can, in extreme cases, it can also be nausea, which causes the patient to, simply arrest consumption of food and water. And then jaundice, which of course is the yellowing of the skin, and in particular, the sclera of the eye. That's where it's easily identified. Let's see. Hepatitis A is not known to cause chronic liver disease, so it is resolvable by our bodies. Hepatitis E, okay, and then also known as enteric hepatitis. In other words, it affects the gut. Okay. What do you need to know? We need to know that this is a problem. Okay. Hepatitis E, if not resolved, it can reach a 20% mortality in pregnant women. Okay. This is supposed to be women and child. Okay, I'll ask this in face-to-face, women and child. So this, in other words, this is something that cannot be ignored. It must be, it has to be managed. Okay, so we just moved from the naked positive single-strand RNA, and now we're moving to the enveloped positive single-stranded RNA. Okay, and that makes sense. Envelope means that it has an envelope, and here's the envelope. It's got a toga. You remember what a toga is? A toga is what the Greeks wore. Okay, every once in a while you hear a toga party. Okay, you're wearing what do you call it? You're wearing a little a cover. Okay, so Toga viridae is enveloped, and flaviviridae, flaviv is Greek for yellow, and that's supposed to allow you to understand that it causes jaundice, so it does affect the liver, okay? And Togaviridae and Flaviviridae are both enveloped. In other words, they have a covering from the host plasma membrane. Their capsid is icosahedral, and it has positive single-stranded RNA. Okay. Coronaviridae. So corona is Latin for crown. Okay. So here the envelope covers the entire virus, but then it has attachment proteins evenly distributed outside of that envelope that makes it look as if it had a crown. And consequently, it's called a coronaviridae. Okay. So one of the things that you need to know is that in order to distinguish coronaviridae from togaviridae is the fact that coronaviridae are also enveloped. However, the RNA inside of it is stored in a helical manner, and that is not true in togaviridae or flaviviridae. So coronaviridae stores their genetic material in a helical manner. Okay, that distinguishes it. Okay, again, I'm only hitting those viruses that are important to us. So now we're looking at West Nile virus and acknowledging that it is a flaviviridae. It's, again, as one of these guys, an enveloped icosahedral single-stranded RNA virus, okay? And it was introduced into the United States in 1999. It was in the news all over at that time. Dengue fever, okay? Dengue fever is not really much of a scourge here in the United States. However, it is in South America, Central America, and even Mexico, okay? So if global warming continues and emerging diseases continue to spread at the rate that they're spreading, the possibility for an epidemic of dengue fever in the United States is plausible. So what do we need to know? We know that there's such a thing as dengue hemorrhagic fever, okay? This happens through reinfection. So dengue hemorrhagic fever, just like we said before, is a consequence of the virus modifying the surface proteins of our tissues and launching an autoimmune response. That's why the first infection doesn't do anything, okay? You need to set up the hypersensitivity in the body, and then it is a second infection, the reinfection, that launches this autoimmune response, which is called dengue hemorrhagic fever. And as the name implies, hemorrhagic means that capillaries start to break down into tissues. You start to bleed from all the orifice, eyes, ears, nose, mouth, and rectum. Okay, so it's a hyperimmune response to reinfection with a dengue virus, and there's no treatment for it. So there's a high degree of mortality associated with hepatitis C. Okay. Still, enveloped positive single-strand RNA viruses. Okay, what do we need to know? Is passed through people that share needles, drug use, organ transplant, sexual activity. Okay, in other words, anything that allows us to share body secretions. And hepatitis C is significant because, again, it causes severe liver damage. In chronic events, total liver failure can take place. And also, if allowed to progress, it can actually end up in cancer. So hepatitis C, a significant problem, okay? Either liver failure or possible cancer. Okay. Now we're moving to coronaviruses. Okay. And let's see. What's the one disease that we are aware of that is caused by coronaviruses, this corona-like halo? And that's SARS, okay, severe acute respiratory syndrome. And again, this is another virus that came from Asia and came to the United States. It was not an epidemic here, but it was enough to be in the news. So there's a coronavirus, okay, corona-like halo. So this is the envelope, okay. You can see the attachment proteins distributed evenly throughout, giving it a crown-like appearance, hence the name coronavirus. There's what people used to look like when SARS was around. Everybody was wearing a mask. Okay, retroviruses. So retroviruses, we've been hitting this pretty hard. The one that we know the most, of course, is HIV, human immunodeficiency virus. But retroviruses are distinguished from the others because they have reverse transcriptase. In other words, they have a protein that allows their RNA to be reverse transcribed into DNA, okay? So retroviruses transcribe double-stranded DNA from single-stranded RNA using the protein reverse transcriptase, okay? That's an important point. And in your assessment, you're going to need to be able to describe what happens with reverse transcriptase. So notice, here's a single-stranded RNA, okay? This is the genetic complement of the virus. Here's reverse transcriptase, okay? And what it does is it uses a little tRNA primer. I don't know if you guys remember when we're talking about DNA replication, we always needed an RNA primer. Here, reverse transcriptase needs a single tRNA primer, and then it produces a complementary strand of single-stranded DNA, okay? Once that DNA is synthesized, then the RNA is degraded, it is broken apart, and then once that negative sense single-strand DNA is synthesized, then it goes back and synthesizes the complementary strand of DNA to end up with double-stranded DNA. That is a lot of things for a single protein to do. This is incredible, okay? What's it doing? Synthesizing single-stranded RNA, that's one thing. And then after the DNA is produced, it breaks down the RNA, okay? That's called exonuclease activity. That's incredible. And then once it has the negative sense single-strand DNA, it synthesizes a complementary strand of DNA to end up with double-stranded DNA. These are three completely different enzymatic activities that are being carried out by a single protein. Very incredible. So you need to wrap your head around that because one of the questions deals with that. And let's see. The last point I want to address is the human T lymphotrophic virus, okay? And in particular, HTLV2, which is responsible for a rare cancer called hairy cell leukemia, okay? So remember, anytime that we say hairy, that typically implies the precipitation of some heavy element, giving the object an appearance of hair. The last time that we talked about this was hairy cell leukoplakia in the tongue. So this is something similar. This is hairy cell leukemia. And let's see, the infections are, well, they're challenging. Okay, that's why we're covering this. So we don't really have a treatment against it. The prognosis of the patient is poor. And the management, not surprisingly, because it is a retrovirus, is very similar to that that's used with HIV. So can you use a treatment for HIV for this? Yeah, and they do. It's expensive. You're talking about interferons. You're talking about antiretrovirals. You're talking about AZT, nucleotide analogs, all these things. They're all very, very expensive. They may or may not work. And so consequently, this becomes an important problem in our lives. And that is it for today. That is it. So with this, you can take your assessment, your little quiz, and I hope to see you soon, okay?